Buongiorno a tutti, a nome del gruppo di lavoro di comunicazione di ESB-ITA. Oggi rinnoviamo un appuntamento con la serie di seminari Inside ESB-ITA, parlando però di ParaView, uno strumento potente per la visualizzazione scientifica e l'analisi dei dati. Vi ricordo che il seminario sarà registrato e sarà pubblicato sui canali di ESB-ITA, poi il link vi verrà inviato nella mail dei seminari, lo trovate anche sui social. Oggi avremo 5 relatori che ci parleranno di ParaView. Il format è il solito, prima una presentazione, poi alla fine potranno essere fatte domande ai vari relatori. E possiamo iniziare e cederei la parola al primo dei relatori. Prego.
Ok, grazie Alessandro. Anticipo solo all'audience che la presentazione verrà fatta in inglese perché una delle presentatrici appunto è di madrelingua inglese, per cui le domande poi credo possano essere fatte tranquillamente poi in italiano per facilitare la discussione alla fine delle presentazioni. Ok. Riuscite a vedere il mio schermo?
Sì.
Perfetto. So, good morning, everyone. Thank you all for being here today. So me and my colleagues that you can see here in the slide today, we will introduce you to ParaView, which, as Alessandro just said, is the world latest software, open source software for scientific data visualization and analysis. During my presentation, I will try to provide you with a brief overview of what ParaView is, how it works, and then I will briefly talk to you about how we can use Python in order to enhance the functionality of ParaView. Then my colleagues will show you how we can use ParaView to analyze both in vivo data and CFD data for cardiovascular applications. So let's start with the basics. What is ParaView? ParaView is a very powerful open source multi-platform tool, which is designed for the interactive visualization and analysis of very complex scientific data and to manage very large and massive data sets. ParaView is developed by Kitware, and it is fully built on top of the Visualization Toolkit Framework, so VTK, which, in a few words, is a C++ library for the computer graphics, scientific visualization, and image processing, which also supports other coding languages like Python and Java. So which are the most interesting aspects of ParaView? ParaView is a very flexible and intuitive software with a very user-friendly GUI, and it is supported by several operating systems. ParaView can also work in a client-server mode and supports the parallel processing to manage very large data sets, and its architecture can be extended and customized via custom plugins that the users can implement inside the software. A very important aspect is that ParaView is based on an interactive visualization pipeline, but it can also support Python scripting in order to automate the tasks that we perform within the GUI. And I would like to focus on these last 2 points in the next few slides. And so, first of all, how does the ParaView pipeline work? The ParaView pipeline basically is the backbone of ParaView. So we have one or more sources that can be represented by basically by the files, the data that we load inside the software, or also by single geometries or topologies. ParaView supports several well-known file formats, and it works with the typical VTK data types, which include structured grid, non-structured grid, polygonal data, and so on. These sources represent the input to the so-called ParaView filters, which are basically numeric algorithms that we use to perform operations on the data. So to edit, modify the data, combine the data, analyze the data, and so on. ParaView offers more than 200 filters, and these are only some of the most popular ones. And here I reported a very simple example of a ParaView pipeline where we have a source, which is in this case represented by a volume grid with the 3 velocity components, for example, of blood. And then we apply on this input data, we apply a first filter, which is a simple calculator filter that we use to obtain the velocity vector starting from the velocity components. And then the output of this filter becomes the input to a second filter, the stream tracer, that we use, for example, to compute and visualize the streamlines of the blood flow field after setting a list of parameters inside the ParaView GUI. And then the final output of our pipeline is basically the mapping or the rendering of the data on our display. In this case, for example, the visualization of the streamlines inside our, for example, arterial model. The second aspect that I wanted to focus on, as I said before, is how we can use the Python language to within ParaView. The first example of this is the programmable filter, let's say a special filter that allows the user to define a custom function exploiting the full computational power of Python, augmented by the visualization toolkit framework. And here I reported a very specific, simple example of how we can use a programmable filter. For example, to clip a volume mesh, a volume grid that in our case is represented, for example, by a vessel lumen, using a closed surface mesh, for example, representing in this case the intraluminal thrombus, because we want to isolate the aneurysm sac from the intraluminal thrombus. So here we have the pipeline to do that, and so we have our two sources in this case that are the volume mesh representing the lumen vessel and the surface grid representing the intraluminal thrombus. And then these two source objects represent the input of our programmable filter, in which basically we write our own Python code using the VTK library functions to perform the clipping of the volume mesh using the closed surface. And so the final output of our filter in this case is the aneurysm sac isolated from the intraluminal thrombus. The second and last example of how we can exploit Python in ParaView is the use of the Python trace and Python shell. So imagine that we have a series of tasks that we want to perform on a single model, and then we need to repeat the same tasks on many other different models. And as you can imagine, if we have to perform these manually within the ParaView GUI, this of course could be extremely time consuming. And so in this case, Python trace is very useful because it allows the user to record all the tasks that we perform within the GUI, and then it generates the corresponding Python script that we can use later in order to, for example, automate all the process and process many other different models, or we can also use the Python scripts to customize our pipeline and adapt it for other analysis, or we can also use it to batch processing multiple datasets efficiently, so outside of the interactive GUI. Here is a very simple example of how we can use the Python trace to automate a series of tasks on many models. For example, imagine that we have three separate surfaces. In my case, for example, the surface of an ascending aorta, an aortic arch, and a descending aorta. And I want to combine and merge these three surfaces in order to obtain one single topology representing the full aorta. And then I want to repeat these tasks for, let's say, n different models of aorta. In my case, it would be for 2 other models for simplicity. So the first step is to start recording a trace within the ParaView GUI that will record all of the operations that I will perform inside ParaView. So after starting the trace, I start to build my pipeline by performing all the tasks. So I start with loading the 3 different surfaces inside the ParaView GUI. So I start with the ascending aorta surface, then I load the aortic arch surface, and then I load the descending aorta surface, and then I take these 3 separate objects and I apply on them a filter called the group dataset, which will group the 3 separate sources into one single object, as you can see in the video. And then on this object, I apply the merge blocks filter, which actually merges the 3 different topologies into one single surface. That is my desired output. Then I can save this merged surface, for example, in a VTK surface file. After that, I have performed all of the tasks on my single model. I can stop the trace, and as you can see, ParaView generates a Python script with all the steps that I have performed, and I can save this Python script, of course, in a Py file. Then the second step is to edit this Python file in an external with an external editor. For example, repeat all of these tasks for, in my case, for example, for other 2 aorta models. And so I can edit my script and extend it and save a new edited Python code that I can simply run within ParaView using the Python shell, simply by clicking on Run Script, browsing, and selecting my edited Python code. And as you can see, ParaView will automatically and fastly process the other 2 models with the task that I have recorded. Okay, so this was a very brief and I hope useful introduction of ParaView and the tool of Python within ParaView itself. And now I leave the floor to my colleagues Selene and Chloe that will show you how we can use ParaView to analyze in vivo for the flow MRI data.
Good afternoon, everyone. Let me share my screen. Thank you, Karol. Screen. Can everyone see my the presenter's view? Sorry, the presentation view? Good.
Yes.
So perfect. And can anyone hear me well? Check.
Yes, we do. Yes.
Great. So good afternoon, everyone. First of all, thanks to the organizers for giving us this chance to show how we combine ParaView tools to process for the flow MRI data, specifically to the aim of using it to enhance our CFD models. As most of you probably know, for the flow MRI is a powerful imaging tool when it comes to visualizing in vivo flow features, but using it, extracting data to be used for CFD model setup and validation might not always be the most straightforward of tasks. So what Chloe and I want to do today is, first of all, I will start with the presentation to give you an overview of how we have been incorporating ParaView in our modeling and model validation workflow to make use of 4D flow MRI data efficiently. And then Chloe will follow with a more hands-on demo to show actually, what steps we take in the hope that helps people replicate our work. Most of the tools we will present today are either already available to everyone open source or will be made available soon. Chloe will also detail this later. So before I start, I just want to make an acknowledgement. So myself and Chloe, Dr. Armour, are here presenting today, but the tools we'll discuss today are a group effort. Now we're spread all over in different labs, countries, and universities, but this is very much a group effort that started from Imperial College London, with people that you see here in the slides that we want to acknowledge, and also we need to acknowledge the various funding sources that over the years helped us build these tools. So as promised, I will start with a quick overview of how our work, our CFD workflow is set up. As everyone, we build our model to be patient specific. So as everyone, we start from medical images, either CT or MRI data. And as a standard output, once you segment this data and reconstruct the geometry, you get an STL file. We also often are lucky enough to have 4D flow MRI data. These come in the standard DICOM format often. And we have an in-house Python tool that helps us convert this data into VTK files that are compatible with ParaView. If you want to know more, you can check this paper where we also, in the supplementary material, made available the code to go from DICOM data to VTK files. Once we have the VTK files from the 4D flow and the STL files, we can open both in ParaView because they're both compatible with ParaView. And what we do then is, more often than not, when you segment data, especially if they come from different modalities, especially if you merge a geometry made from CT data with 4D flow, they're not registered. So the first step we take in ParaView is registering our geometry model with our 4D flow data to make sure the coordinate systems overlap. And this is quite a delicate step to make sure the models are reliable, but also an important step because we use it then to extract boundary condition and later on you'll see to validate the model. Once we have registered geometry, then we proceed with the meshing, the discretization of the fluid volume, and to set up our fluid solution. What we do at this point is we take advantage of the co-registration between the geometrical data and the 4D flow MRI data to extract the patient-specific boundary condition that then we use in our model. Specifically, once you have a co-registered information between the Arctic geometry and the 4D flow MRI data, you can use this information to, for instance, set up cross-sectional planes in ParaView to extract flow rate information at the inflow or at the outflows. And this is an information that we use to set up our outlet boundary condition. Imagine you can extract the patient-specific flow waveforms at the supraortic branches and descending aorta. That is something you can either directly impose as boundary condition, or we personally prefer to use these in pair with pressure data to set up Wien-Kessel boundary condition. Now, I don't have time to go into details, but you can find the details of how we do that in the papers I cite along the presentation. On top of this, since we have a registered geometry with the 4D flow data, we can also use this information to extract patient-specific velocity profiles that are also time varying, as the 4D flow data provides also the time dimension. What we do specifically when we model the ascending thoracic aorta, for instance, where multiple works in the past 10 years have shown that the inflow profile, so the profile dictated by the shape of the aortic valve, is one of the most important factors to determine the fluid features, the blood features in the ascending thoracic aorta and aortic arch. We use this information to extract patient-specific velocity profiles that we impose as inlet boundary condition. And this is all done with a combination of ParaView and Python scripting. If you want to access the scripts and see how they work, Chloe will also show some of these later on. You can check the supplementary data of this work. Once we have our boundary condition and our meshed model, we can set up the solution. We, of course, run the solution using the standard solver setting in CFX Fluent or Vascular, depending on the aims of the works. And once we have our solution, we don't immediately start processing the data, but what we do is, sorry, my computer is on. What we do is then we circle back to the 4D flow data to verify and validate our model. So we have a loop system where we run our models and we compare our results against 4D flow data before moving on to comparison as a way to validate, to make sure that our CFD results are in line with the physiological reality as described from the 4D flow data. And this we do once again in ParaView, as Chloe will detail soon in her demo. Then, of course, we move to post-processing once we're confident that our model reproduces to the best of our capabilities the reality. So here I have a couple of examples of how we have been doing this in the past. We started back in 2019, where we could only do a very qualitative comparison between our CFD results and the 4D flow MRI data. Later on, thanks to the paper I cite here, which is not from our lab, but is a great paper, and I would recommend everyone to check this out. This paper inspired us to develop more quantitative ways to compare our CFD results to the 4D flow MRI data. So what we did was we started in ParaView. We implemented a pipeline to downsample our CFD data to match the 4D flow MRI resolution. This allows us to extract, to obtain a pointwise correspondence between the predicted velocity from the CFD and the 4D flow MRI data, and to make statistical comparison. Here you see it in the form of correlation test between our predicted results and the 4D flow MRI results. And this we did with, let's call it normal CFD, with LES models, where of course this becomes even more important and more challenging actually. And recently we started doing these also with FSI results, where of course the challenges increase because we have moving walls also from the FSI simulations on top of the CFD. We recently published this work where we implemented a more qualitative comparison. And now, these are very preliminary data with Giulia Luraghi, and thanks to the brilliant Viola, we are trying to push these forward and also implement a more quantitative comparison between FSI results and 4D flow data. And this we all do in ParaView. So after this hopefully quick overview, I want to leave the floor to Chloe, who will take this workflow and show you key steps and how we do them in practice in ParaView.
Wonderful, thank you, Selene. So as Selene said, I'm just going to show you a couple of the key parts of that workflow that we conduct in ParaView, with a bit of a demo as to what is going on. So just to start with, the first thing we're looking at is processing and trying to extract some boundary conditions from the 4D flow MRI data we have. So first of all, just for those of you who haven't seen 4D flow MRI data before, this 3D volume is what will be the output of the Python script, which we've referenced. We have papers for, and this code to output this VTK file is open source currently. And what this does is it takes the raw DICOM files from the 4D flow MRI and processes them to produce these velocities. So when we start to look into the block we have here, we can look at any of the three slices. And what we're looking at here generally is the patient's body. In the bright red is where we're picking up the strong velocity signals. So we've got the descending aorta here, areas of the heart in the middle. And this patient specifically, we were actually looking at their pulmonary artery, which is extending up on the left-hand side here of the image, as this is a study I'm working on looking at pulmonary hypertension. And when we have the 4D flow MRI data, the great thing about it is that it's analysing the patient's velocities throughout the cardiac cycle. So up in the top here, we can change the time, and this is looking at all the time points that have been recorded. So generally, the temporal resolution of a 4D flow scan is, in this case, is 24 time points, 25 actually, because it starts at 0. 25, 30 time points is quite a good resolution. You don't get too much more than that usually, due to the limit of the patient being able to stay in the scanner for that long. So the first thing there is we have our 4D flow data. And then what we want to do is align a segmentation with this so we can build our CFD model. So the first step, if we're looking at bringing in a geometry, is when I open it here, I can't really see it. And if I extend my screen view, it's popped up. What's happening here is actually this geometry is 1,000 times bigger than the 4D flow data. And that's because the 4D flow data Python scripts have been set up so that all the units are SI units, meters per second. But often when you segment a CT or an anatomical MRI scan, your geometry will come out in millimeters. So the first thing is simply scaling your geometry down. And we can use ParaView's transform function, so either finding it through any of the filters, listed all here, or control spacebar and you can search for any function you're looking for. So with a transform function, you can either translate, rotate, or scale. So the first thing is just scaling it down to the right size. So when we do that, you can see for this patient, the scan is actually not in line. This is the pulmonary artery here. We can see with the main pulmonary artery coming out of the right ventricle and splitting into the left and right pulmonary arteries. And it should be in line with the velocity data that we're seeing here. So actually this geometry came from an anatomical scan that was taken right before the 4D flow scan was taken. So the patient was actually in the same machine in the same position. But what can happen is when you're processing the MRI data, basically the BTK files can be flipped and moved slightly. So in that case, if your geometry does come from a scan that was taken in the same machine at the same time, you can actually just first of all import the full 3D volume of acquisition. Again, this is just transformed to be on the correct scale first of all. And with any item you have open in ParaView, you can look at the information and look at the bounds. So this will work if, as I say, it's from the same machine at the same time of the same patient. You can look at the bounds. You can look at the bounds of the one you're trying to register to, and actually then you can perform an exact transformation to set them up in line. And if you do this, when you perform any transformation, so I've specified a specific translation and rotation to match this, you can then copy these properties and apply them to any other transform on a different component, and that will shift the artery to be in line. So that works well if, for example, in the 4D flow MRI case, we have an anatomy scan first, but quite often what we're working with is possibly a CT scan taken on a slightly different day, different machine. In that case, you may open your VTK files here and your CT scan opens in a completely different part of the screen. You don't have any key bounding points that you can just numerically shift towards, and that does become more of a manual registration. So again, you can just play around with the numbers in the rotate and the translate, or you can simply pick up the boxes, drag and move it, etc. So when it comes to doing it more manually, obviously to try and get it as close as possible, we really start looking at trying to identify some key anchoring points. So if it's in the aorta, we will try and match up specifically where we can see the coronary arteries and the 3 aortic branches. Here in the pulmonary artery, I'm looking specifically for that bifurcation point. And it does become a bit trial and error, a bit manual, but that's especially important where Selene mentioned that once we do the CFD simulation, we're reverting back and we're iterating, we're checking how well matched the results are and if we need to make any modification. So once we're happy with the alignment, we can now take this geometry and simply just save it from ParaView with file save data, save it as an STL. We can then go on to cut our inlet plane, cut our outlet planes, set up our CFD simulation however we want to, and actually run that to achieve the CFD solution. So obviously Selene went over that workflow. I'm not going to go into those points because that's not the ParaView steps. But if we then come to think about, we have run our CFD simulation and we want to verify and validate the results we have got against the 4D flow MRI data. So the first thing is opening here on the left. I've opened my CFD simulation results. You can see now there's 65 time points. This patient's cardiac cycle was about 0.6 seconds. So whatever your temporal resolution you want to be saving at is. And from that first geometry, I've cut an inlet plane within the pulmonary artery. So I'm not including the right ventricle just now. And I've got my 2 outlet planes. To then go on to look at how we can compare that to the MRI data, we want to segment out this exact region from that full cube. And for that, we have a Python script. Again, all our tools that we're using alongside ParaView here are developed in Python that allows us to input the full VTK block here. So we input this full VTK block. We input the STL file that we've used in our CFD simulation, and it will output the MRI data, 4D flow MRI data, specifically in that region that's aligning. So in this set, if we turn both of them on, you can see they are on top of each other. They're well aligned. You'll notice, obviously, the image resolution of this is much larger. That's one of the limitations of the 4D flow. That's why we have developed this workflow of using CFD to enhance our MRI results. So with that, we can just start with some first qualitative visualization. So for both cases, we can look at just plotting some slices. In this case, I have now selected for the CFD the 10th time point because with the flow information I have, I know that's peak systolic flow. I have opened the 4th time point of the MRI data. Again, I know that's peak systolic flow based on the analysis. So we can start with just some visualization, seeing where that CFD has clearly quite accurately captured some high velocity patterns. We can look at plotting some streamlines for comparison as well. Again, all of these are created with functions in ParaView that were demonstrated earlier. So this just allows us to start our qualitative comparison. And then the final step we look at doing, which Selene mentioned, is the more quantitative side of things. So to do that, as the MRI is the lower resolution, we start with downsampling our CFD data. So the filter we use in ParaView for that is called resample with dataset. So if I have my CFD data selected and I search for resample with dataset, there are just 2 things you need to define or you need to choose. You need to choose what your source data is. So this is my NSIGHT CFD file. My CFD was run in ANSYS CFX here. So this is the version that works with ParaView. I then select what my destination mesh is, which in this case is the VTK file for my MRI data. This says patient 25, segmented CFD. That probably should have named it something else to be less confusing, but that's me telling myself I have segmented this to match the CFD. This is not CFD data, this is MRI data. So our source data is the CFD, the destination mesh is our MRI VTK. When we do that, it will create one item called resample with dataset that turns on 3 times every time you do it, so don't be confused by that. But we now have our CFD data, which looks the same resolution and is the same resolution as our MRI data. And with that, you can then save these files. We save them just as CSV files. So file, save data, and save as a CSV. You save your CSV of your CFD data. You save the CSV of your 4D flow MRI data, making sure you have chosen the time point correctly, that you're comparing peak systole from CFD and peak systole from MRI. And those two CSV files go into another Python script we've developed to do the quantitative analysis. And just to demonstrate some of the results you can get, some of these pictures Selene had as well. So we can be plotting scatter plots of CFD versus MRI for each 3 velocity components. We can look at the Bland-Altman plots as well to more easily quantify how offset these correlations are. And then just looking at your general Pearson correlation coefficients for each component. So the Python codes for this specific quantitative analysis and for segmenting the 4D flow data to match the CFD, etc., are currently not available with the original code to create these VTK files, but they will be coming out shortly with a new paper that it's on its way. But if you have any questions before then, more than happy to answer anything by email. But with that, we will conclude there. And thank you very much for the organisers as well for the opportunity to show this.
Thanks. Okay, so I can share my screen. Okay, do you see my presentation?
Yes.
Okay, so we'll introduce some important post-processing techniques that can be performed using ParaView, starting from CFD data from CFD simulations. So first, I will show you 2 different techniques to characterize the dynamics of vortex structure in a complex geometry. Then I will show you how to perform particle tracking in ParaView. In particular, how to compute path lines and Lagrangian coherence structures. So we start from the first technique to characterize vortex structure, the Cook criterion, which is a method used in fluid dynamics to identify the presence of vortices in a flow field. So first, we have to import the file containing the velocity vector. Then we can select a filter called gradient. First, we have to choose the array we want to analyze, in our case, the velocity. And with this filter, we can compute the gradients, the divergence, the vorticity, and also the Cook criterion. So we have to enable the Cook criterion option and then click on apply. The output of this filter will be the Cook criterion. So we can visualize the Cook criterion using the, for instance, isosurfaces, which are 3-dimensional surfaces representing point of a constant value. So to do that, we can select the filter contour, which extract isosurfaces from scalar field data. So we have to select to choose the scalar variable we want to contour, and then we have to write the constant value. Of course, varying the value, we will visualize different isosurfaces. So there are different parameters, different options to enable or turn off. For instance, with compute normals, a scalar array containing a normal value at each point in the isosurface will be created by the filter. So this is an example of the evolution along the cardiac cycle of the vortex structure inside the intracranial aneurysm model using the Cook criterion filter. In this example, the isosurfaces are colored by the velocity magnitude. Okay, now I will show you how to use a Python calculator filter to compute quantities that are not available in ParaView. For instance, the swirling strength, which is a scalar measure of the local swirling rate inside the vortex. So to obtain this quantity, we have to calculate the absolute value of the imaginary part of the complex eigenvalues of the velocity gradient tensor. So in ParaView, there is not a filter to compute this scalar quantity, and so we have to use a Python calculator. So as before, we import the file containing the velocity data. Then we select the filter gradient, enabling the option to compute gradients. In this way, we obtain the velocity gradient tensor, so the 9 components of the velocity gradient tensor. Now, the output of this filter will be the input of the Python calculator filter. So in this section, we can write the Python code using the NumPy library to compute, in this case, the imaginary part of the complex eigenvalue of the velocity gradient tensor. Then we have to write the name of this new variable and click on apply. The output will be this new quantity. So we can see in this example the swirling strength in abdominal aortic aneurysm along the cardiac cycle. Now, to avoid writing the Python code every time we want to compute the swirling strength, we can create a custom filter. So first we have to select all the variables we need to compute the quantity. Then we can go to Tools and select Create Custom Filters. We write the name of the filter and then we click on Finish. Finally, to save the custom filter, we can go again on Tools and select Manage Custom Filter and then Export. Then in this way, the new filter will be visible along all the other filters, and we can apply the filter directly to the velocity data. So in this example, this is an example of the swirling strength isosurfaces in an aortic model with a mechanical aortic valve at 5 different time instants along the cardiac cycle. Okay, now I will show you how to compute pipelines in ParaView, which are used to visualize the motion of individual fluid particles over time. So as before, we start with time-dependent velocity data. So if we have different files in a folder corresponding to different time steps, ParaView should detect the series and load them as a unique dataset. So we import the velocity and we select the filter particle path. So we need to specify the input, in our case are the velocity data, and then we need to specify the initial locations where the particles are released. So the seed source can be, for instance, the inlet of our model or a different slice or point inside the model. So the termination time determines the maximum time for which the particle paths are computed. Then force reinjection every n steps option refers to the number of time steps after which new particles will be reintroduced at the seeding points. So if this value is equal to 0, particles are only injected at the beginning. Otherwise, if this value is a positive number, ParaView reinject a particle after the specified number of time steps. So after the specified time, we obtain the path lines. So in ParaView, there is also another way to compute pipelines. In this case, we need to combine two different filters. So as before, starting from the unsteady velocity data, we select a particle tracer filter. As before, we need to specify the input, the seed source, and also if you want the particle to be reinjected after n time steps. Now, from this filter, we obtain the position of the particles over the time steps. So the output of this filter will be the input of a new filter called temporal particles to pathlines filter. This filter links the particle positions over the time steps to form continuous pathlines. So with the mask points option, we can control the number of particles to be traced. With the mask track length, we can impose the maximum number of time steps that a particle will be traced. With the max step distance controls the maximum distance between 2 points in a pathline. And finally, since particles move across different time steps, ParaView needs a way to track each particles, and the ID channel array option is used to identify each particle over time. So in this slide, we can see initial distribution of particles on a cross-section in an intracranial horizon model at time 0. Then, after n time steps, we can see the trajectories of each particle over time. So, moreover, we can use the particle tracer filter to visualize the motion of fluid particles over time. We can color the particle with the velocity or using a different quantity in order to have more information. For instance, in this example, the particles are colored by using the Swirling strength. Finally, it is possible also to visualize the pathlines over the time. Okay, so to conclude, I will show you how to compute with ParaView the Lagrangian coherence structure, which are material surfaces that are dominant in attracting or repelling fluid particles over a time interval. So in this example, we will compute the Lagrangian coherence structure of time-dependent Washer stress on the luminous surface of an artery. So we apply the particle tracer filter to the Washer stress data, and we consider as seed source the entire luminous surface of the model. Now, the final position of particles after the first cardiac cycle will be the starting position for the second cardiac cycle, and we apply again the particle tracer filter, and so on until the particles stop moving. So this is an example of the initial tracer position on the luminous surface of a carotid bifurcation model, and the attracting Washer stress Lagrangian coherence structure traced after 10 cardiac cycles. Okay, this was my last slide, so I pass the floor to Maurizio.
Hello everyone. Let me share my screen. Okay. Okay, do you see my presentation? Yeah, I think yes. Okay.
Yes.
Let's very quickly. Let's see how to extract Washer stress from velocity data. Okay, let's start from mathematics. Here we have the definition of Washer stress. Let me. Here the mathematical definition of Washer stress from velocity field, and we have two ingredients, which are the gradient of the velocity here defined here, and the normal and the surface normals. After several steps, we can obtain Washer stress components and then Washer stress vector. This is from a mathematical point of view, and let's see how to implement it in ParaView. So velocity is defined as velocity x, y, and z in ParaView. Then the first step is to compute from volume data, which we imported in ParaView, the velocity gradients. And we see that we basically have to use the gradient filter and activate only compute gradient. Then we have here the structure of gradient and the parallel with the mathematical defined gradient of the velocity vector field and the gradient name here, tensor in ParaView. Then after that we have the first ingredient, which is the gradient of velocity field. Then as a second step we need to extract surface, remove caps, and compute the surface normals, which are the second ingredient. The first step is performed with the filter extract surface. The second step, the caps removing, is here performed exploiting that in CFD simulation velocity is equal to 0 at the wall. So I basically used a threshold filter on the velocity magnitude. And finally, with the filter surface normals, we can compute the normals, which are defined as normals x, y, and z. And here I activated the command flip normals to have the direction outside from the wall of the normals. And then we have the two ingredients, and we can compute the three components of the velocity of the Washer stress vector field, which are Washer stress x, y, and z. Here I used the filter calculator, and you see that here the translation of the mathematical formulation to the ParaView formulation using normals x, y, and z, and gradient 0 to 8. Then finally we can compute the Washer stress vector field combining the three components with another calculator filter. And here you see the Washer stress magnitude and the Washer stress vector field visualized using the filter glyph. Then we can finally save the surface, and we can select the array we want to export. Here I selected Washer stress, and it's possible to export just one time step or all the time step of the simulation. So what we obtain is Washer stress vector field over time. And as you can see, the Washer stress vector field change during the cardiac cycle, both in magnitude and in direction. So one important thing is to synthesize the information given from Washer stress. The simplest way to synthesize this information is to average in time the Washer stress magnitude with the descriptors time average Washer stress. In ParaView, we just have to compute the magnitude of Washer stress using the filter calculator, and then average in time this new scalar using the filter temporal statistics, activating compute average, and then we obtain the time average Washer stress. Then if we want to characterize Washer stress multidirectionality across the cardiac cycle, we can compute the transverse Washer stress, which is a little bit more complicated. we start from the inner part of the equation. So we first compute the washer stress vector field average in time using again the temporal statistics filter. Then we can compute this ratio and the cross product with the surface normals, which are the ones we previously computed. Then we need to use this filter called append attributes, because the output of the filter temporal statistics lost the information about instantaneous washer stress. Then we need to combine the time average filter with the instantaneous washer stress, which is the file I uploaded. Then we can perform this scalar product, this dot product between washer stress and the results of this cross product. And then we use again temporal statistics to compute this outer integral in time. And what we obtain is this map, which, as you can see, present higher value where the washer stress change the direction over the cardiac cycle. So it's more multi-directional during the cardiac cycle. Finally, we can also compute washer stress topological feature, in particular the divergence of normalized washer stress identifies with negative values washer stress contraction regions, and with positive values washer stress expansion regions. So as a first step, with the filter calculator, we can normalize washer stress, and then using again the gradient filter, we can compute the divergence. Here in this video, you can see how change during the cardiac cycle the washer stress contraction and expansion action, and how it is identified by the positive and negative values of the divergence. And finally, we can also characterize this expansion and contraction action during the cardiac cycle using the topological shear variation index descriptor, which basically quantifies the amount of variation in washer stress contraction and expansion action exerted on the endothelium along the cardiac cycle. We use the filter temporal statistics, and in this case we select compute standard deviation, and as you can see here, the descriptor identifies the regions where the divergence of the normalized washer stress changes more during the cardiac cycle. And I think this is all. And so thank you for your attention. I hope to stay in time. Ok. Ok, penso che potremo passare alle domande.
Thank you for all the speaker.